Good day, class. It's me again, your Lady Alchemist. Please don't forget to like, share, and subscribe to my channel. So for today's video and lesson, we're going to discuss the Hund's rule of multiplicity. And for our objectives for this day, is to differentiate the Aufbau principle, the Pauli exclusion principle, and Hund's rule of multiplicity. So without further ado, let's get started. But before that, let us first define the term orbitals. Orbitals are atomic orbitals described where an electron is likely to be found in an atom. Every atomic orbital is associated with 3 quantum numbers, and these quantum numbers are the N, L, and ML. Atomic orbitals have distinctive shapes. All are centered on the atomic nucleus. The most commonly encountered orbitals in elementary quantum chemistry are the orbitals corresponding to the s, p, and d subshells. These orbitals are named the s, p, and d orbitals. In the ground state of heavier atoms of f orbitals are also encountered. Now let's take a look at the first orbital, the s orbital. All s orbitals are spherical and can hold up to 2 electrons. The lowest energy orbital of all orbitals is the s orbital or the 1s orbital. When it holds 1 electron, it is written as 1s1. When it holds 2 electrons, it is written as 1s2. Here is your illustration of the s orbital. Next is the p orbital. The lowest energy p orbitals, the 2p, are shown below. They sit at right angles to one another and are centered on the nucleus. Since their length can be aligned with x, y, and z axes, they are individually described as the px, py, and pz orbital. So the p orbital can only hold a maximum of 6 electrons. Next is the d orbital. The lowest energy d orbitals, the 3d, are shown below. There are 5 d orbitals, each of which can hold a maximum of 2 electrons. So in total, the d orbitals can accommodate up to 10 electrons. The d orbitals are the dxy, dxz, dyz, dx squared, y squared, and dz squared. When 1 electron is accommodated by the 3d orbitals, it is written as 3d1. 6 electrons would be written as 3d6. 10 electrons would be written as 3d10. The d orbitals are named in the relation to the x, y, and z axes. Once again, the different colors indicate the different phases of the wave function. This orbital is in the xy plane. The 4 lobes do not touch the axis. They occupy the 4 quadrants between the x and y axes. Next, let's move on to the f orbitals. At the 4th and higher levels, there are 7 orbitals in addition to the 4s, 4p, and 4d orbitals. Counting the 4s, 4p, and 4d orbitals, this makes a total of 16 orbitals in the 4th level. They have even more complicated shapes. S, p, d, and f orbitals are available at all higher energy levels as well. Fortunately, you will probably not have to memorize the shapes of the f orbital. Just remember that there are 7 orbitals in each level from level 4 and onwards. So, here are the illustration of the different orbitals. So you have the s orbital. Remember that the orbital for s is only 1, 3 for p orbital, 5 for d orbital, and 7 for the f orbital. Next is, let's move on to differentiating the Aufbau principle, the Pauli exclusion principle, and the Hund's rule of multiplicity. What is Aufbau principle? The Aufbau principle states that the electrons fill the available orbitals from the lowest to highest energy level. In the ground state, all the electrons are in the lowest possible energy level. Also, electrons will successively occupy over the available orbital in order of increasing energy level. That is why, in our previous lesson, you learn how to use the electron configuration, or you learn how to use the mnemonic device. And again, in this pattern, you have to fill in the electrons starting off with the lowest energy level, and that is the 1s, before you move to the next higher energy level. How about the Hund's rule of multiplicity? The Hund's rule of multiplicity states that the electrons must be placed into the orbitals in such a way that no pairs are put together unless necessary. That is, single electrons must be placed into the boxes first and then paired up if necessary. In other words, when an electron enters a sublevel containing more than one electron or one orbital, they will spread out over the available orbital with their spin in the same direction before they paired up with the opposite spin. As you can see in the sample 7 nitrogen, the electron configuration is 1s2, 2s2, 2p3. A single box here represents an orbital, and the arrow inside the box represents the number of electrons. According to the rule of the number of electron, according to the rule of Hund's rule, the spin and arrow, which is also the electron, will spread out over the available orbital before pairing up if necessary. So as you can see in the 2p3, in the sample, the spin inside the boxes are spread out. So each box has only one spin or one arrow. So remember that there will be always one orbital, that is s orbital, then 3 for p orbital, you have 3 orbital for p, d is 5 orbitals, and you have 7 orbitals for f. Since you have only one orbital for s, and the maximum number of electron that can hold the s sublevel is only 2 electron, can also consider that there will be a maximum of 2 electron for the first box or first orbital of s. It should be in opposite direction, so the spin inside the box represents the number of electron. An orbital filling diagram is the more visual way to represent the arrangement of all the electrons in a particular atom. In an orbital filling diagram, the individual orbitals are shown as square or boxes, as you can see in your screen. And orbitals within a sublevel are drawn next to each other horizontally. Each sublevel is labeled by its principal energy level and sublevel. The electrons are indicated by arrows inside the box. An arrow pointing upward indicates one spin direction, while a downward pointing arrow indicates the other direction. And take note that in the s orbital can only hold a maximum of 2 electrons. Remember that the p orbitals can only hold 6 electrons. The d orbitals can only hold 10 electrons, and the f can only hold 14 electrons. The Pauli exclusion principle states that the electrons must be placed in opposite spin, which means that there should be an up and down spin always together. So in other words, the electrons occupying the same orbitals must have opposite spin. As you can see in the example for neon, the atomic or the electron configuration of neon is 1s2, 2s2, and 2p6. So if you take a look at the spin inside the orbital, it is in opposite direction. So according to Pauli exclusion principle, that electrons must be placed always in opposite spin. Since the electrons found in the box is just a representation of orbital, the spin inside the box must be in opposite direction. One spin must be in upward position and the other one is in downward position. So here is your example. Number 1. Lithium. The electron configuration of lithium is 1s2, 2s1. To write the orbital diagram using Hund's rule of multiplicity, you have to first write the electron configuration. To represent the s orbital, again you can use a box. The total number of spin inside the box is also the total number of electrons or the atomic number of an element. So which means that if you're going to count the number of spin inside the box, you have 1, 2, and 3. The atomic number of lithium is also 3, and so as the number of electrons. Next example, arsenic. The atomic number is 33. Meaning, in a neutral atom, the number of electrons of arsenic is also 33. First is to write the electron configuration, which is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p3. Using the orbital diagram of Hund's rule of multiplicity, remember that 1s orbital or 1 orbital for s, and to represent that you can use a single box for 1s2, then put 2p or 2 spin or 2 arrow with opposite direction following the rule of Pauli exclusion principle, which states that the electron should be in opposite direction. And since you are writing the electron configuration, you are actually following the rule of Aufbau principle because you started occupying the lowest energy level, which is 1s2, and so on and so forth. So remember that for the S sublevel, you're going to represent one box to represent the S sublevel. For P, you have 3 boxes. D, you have 5 boxes. And the number of spin in opposite direction inside the boxes is always the same with the total number of electron of a given element. So, is there any questions? That's all. Thank you. I hope you learned something new today. So, we'll see you on my next video. Bye!